Steady states and stability analysis of the Nicholson-Bailey model. The Nicholson-Bailey model is a classic model used to describe the interactions between a host and a parasitoid population. It is defined by the following discrete time equations. Ant plus 1 equals A times Ant times E to the power of negative A times PT plus 1 equals C times Ant times 1 minus E to the power of negative A times PT, where Ant is the population of the host at time t, PT is the population of the parasitoid at time t, A is the reproductive rate of the host, A is the searching efficiency of the parasitoid, and C is the average number of viable eggs laid by a parasitoid per host. The steady states occur when Ant plus 1 equals Ant and PT plus 1 equals PT, leading to the following system: N star equals A times N star times E to the power of negative A times P star equals C times N star times 1 minus E to the power of negative A times P star. The trivial steady state is N star equals 0, which represents the extinction of the host population. For a non-trivial equilibrium where both species coexist, solving for P star leads to A times E to the power of negative A times P star equals 1, taking the natural logarithm on both sides. Negative A times P star equals the natural log of 1 over A, P star equals negative the natural log of A divided by A. From the second equation, N star equals P star divided by C times 1 minus E to the power of negative A times P star. By substituting P star we get N star equals negative the natural log of A divided by A times C times 1 minus A to the power of negative 1, which represents the equilibrium population densities of both species. To analyze the stability of the equilibrium, we compute the Jacobian matrix of the system. J equals the matrix with partial derivatives of F with respect to N, partial derivatives of F with respect to P, partial derivatives of G with respect to N, and partial derivatives of G with respect to P, where F of N and P and G of N and P represent the right-hand sides of the system equations. After computing the Jacobian at the equilibrium N star and P star, the characteristic equation is found to be lambda squared minus the sum of J11 and J22 times lambda plus the product of J11 and J22 minus the product of J12 and J21 equals 0. By solving for the eigenvalues lambda, we can determine the stability. If the absolute value of lambda is less than 1, the equilibrium is stable. If the absolute value of lambda is greater than 1, the equilibrium is unstable. For the Nicholson-Bailey model, it has been shown that A times the natural log of A divided by A minus 1 is greater than 1. This condition is never satisfied for any value of A, meaning that the equilibrium is always unstable. This implies that any small deviation from the steady state will lead to oscillatory divergence, rather than a stable population balance. Below we provide implementations in MATLAB, Python, and Maple to visualize the population dynamics of the Nicholson-Bailey model. Below we provide implementations in MATLAB, Python, and Maple to visualize the population dynamics of the Nicholson-Bailey model. Percent Nicholson-Bailey model simulation: A equals 2, A equals 0.1, C equals 1, N0 equals 10, P0 equals 5, T equals 50, percent time steps N equals zeros, 1T, P equals zeros, 1T, N1 equals N0, P1 equals P0, for T equals 1 to T minus 1, Nit plus 1 equals A times NT times X times PT, PT plus 1 equals C times NT times 1 minus X times PT, N figure, plot, 1:T N R, line width 2, hold on, plot, 1:T P B, line width 2, X label, time, I label, population, legend, host, N, parasitoid P, title, Nicholson-Bailey model. Import numpy as np, import matplotlib.pyplot as plot. A equals 0.1, C equals 1, N0 equals 10, P0 equals 5, T equals 50 hash. Initialize arrays N equals npot zeros T, P equals npot zeros T, N0 equals N0, P0 equals P0 for T in range T minus 1, Nt plus 1 equals A times and times NPX, A times P, P plus 1 equals C times and times 1 minus NP dot X, A times P. Hash plot results pilot.figure, fig size equals 8,5, pilot.plot range T, N, R, line width equals 2, label equals host N, pilot.plot range T, P, B, line width equals 2, label equals parasitoid, P, docs label time, I label, population, legend, title, Nicholson Bailey model, show. A colon equals 2, a colon equals 0.1, C colon equals 1, N0 colon equals 10, P0 colon equals 5, T colon equals 50, N colon equals array, 1 T fill equals 0, P colon equals array, 1 T fill equals 0, N 1 colon equals N0, P 1 colon equals P0, for T, from 1 to T minus 1 do int plus 1 colon equals A times int times exp, a times Pete plus 1 colon equals C times int times, 1 minus exp, a times Pete, N do, plots display, plot sec T ent, T equals 1 T, color equals red, thickness equals 2, plot sec T Pete, T equals 1 T, color equals blue, thickness equals 2, title equals Nicholson Bailey model, labels equals time population, legend equals host, N, parasitoid, P. Below is a bifurcation diagram showing the unstable oscillations predicted by the model. I'll generate a figure with colored trajectories using Python to demonstrate the dynamics. The plot above illustrates the unstable oscillations in the Nicholson-Bailey model. As predicted by our stability analysis, the populations of the host and parasitoid do not settle into a stable equilibrium. Instead, the fluctuations grow over time, leading to either extinction or extreme oscillations. This instability is one of the primary criticisms of the model, as real-world host parasitoid systems tend to be more stable. This leads to the development of modified models, incorporating factors like density dependence or spatial distribution to introduce stabilizing mechanisms.